I will talk a bit about my own experiment because during my PhD I did an ethics assessment of nano microplastics in Dutch freshwater systems, and I thought it would be interesting for you to have a look to how these experiments are done, so how an effect assessment can be done. So, in this figure, you can see what Bart just explained to you, how primary microplastics can enter the aquatic environment, and also how secondary microplastics can be formed due to the degradation of bigger plastic particles or bigger pieces. And as he also explained, these plastic particles will be found in different compartments of the aquatic system depending on this vertical transport. And in these different compartments, they will be exposed to different organisms. For instance, zooplankton and phytoplankton can be mostly found in the water surface and will encounter the plastics that are there. And plastics that sink to the sediment will be in contact with benthic invertebrates such as this crab or this crustacean, and also benthic fishes, for instance, while pelagic fishes will encounter plastics in the water column. What I also found interesting from this graph is that it shows what are the sources of microplastics in the ocean, which I think I didn't mention. And you probably have heard about the importance of microplastics in cosmetics, but as you can see, the amount of microplastics in cosmetics is actually very low, comparing it with other sources, such as the entrance of cartile particles in the environment. So if we want to reduce the entrance of microplastics, we also have to look at these other sources. This figure shows different trophic chains in the ocean, which start with the base of these trophic channels with zooplankton and phytoplankton species, and which end up with top predators such as marine mammals. And what I want you to see here is that in all these trophic levels, microplastics have been found in the field. So zooplankton species have been sampled and microplastics have been found inside these organisms. Also in benthic invertebrates such as mussels or worms, also in fish and in birds, and even in whales. And when it comes to nanoplastic, there is no field data available yet because current technologies do not allow the detection of the nanoplastics in the biota yet. Last year, for the first time, they were able to detect them in the ocean, in seawater. So maybe over a few years, they will be able to, or we will be able to detect them in organisms. I'm going to give you several examples on different group of species. But what I want you to know is that I've taken it from different studies, and in these different studies, they use different plastic types. So they use nanoplastics or sizes, microplastics with different sizes or shapes or charges, not only different species. So these studies are not comparable. And I will start with phytoplankton, which are the microalgae. And as you can imagine, they are not animals, so they will not eat the plastic. But the way they interact with this plastic is by heteroaggregation. So these nanoplastics and microplastics can get attached to the surface of this algae. And this can be very easily seen here. So this is the microalgae, and these are 1 micrometer microplastics that are attached to the surface. And here is our green algae, all surrounded by microplastics and nanoplastics. And this interaction has caused growth inhibition, reduced chlorophyll content and photosynthetic efficiency in several species. And when it comes to zooplankton, I wanted to show you a video that you might have seen before where they added microplastics to zooplankton so that you have an idea of how this can go. So this video illustrates a bit how the zooplankton can ingest plastics, and they can also digest them afterwards. But what I want you to show you is also that this is not very environmentally realistic. So in nature, the zooplankton will not be surrounded only by this huge amount of microplastics. So also when looking at studies where they fed this zooplankton species with a lot of plastic, they were able to see where they were going, and yeah, you can see in the gut of the species how they accumulate, and also that they cause quite severe effects on health. This is the case of the nanoplastics, and they show that the mortality was found for several species, reduced fecundity and reduced growth rate, gross production, which is the reactive oxygen species production, and the increase in molting events. But most of these studies use concentrations far higher than what can be found in the environment. So please don't be scared. When it comes to microplastics, most studies saw a reduction in their feeding and a reduction in their fecundity. So it seems that the effects of microplastics are less severe than the effects of nanoplastics. When it comes to benthic invertebrates, it has been found reduced feeding activity in the mussel Mucilus edulis, embryo toxicity on the sea urchin Paracenterotus lividus, and in the case of this oyster, they found that they were able to ingest the particles, but they didn't determine the effects, which happened also in several studies where they evaluated ingestions but not effects. And in the case of microplastics with the same mussel Mucilus edulis, we see that they were able to ingest them and they caused cell inflammation. In the case of the worm, lapworm Adenicola marina, there was energy reserve depletion. And in the case of the isopod Pithecia marginata, they found ingestion as well, but they didn't find any effects on this species. And they also tested several fish, and I wanted to show you a video on how they tested the effects of microplastics on this fish species, so that you have an idea on how this can be done. So in this case, what they found when they added microplastics to the column was that there was a reduction in the swimming velocity and the resistance time of this species. Also, several studies have looked at the trophic transfer of microplastics, and what they did was to load the organisms, in that case zooplankton and here a mussel, with microplastics, and then they exposed this species to a predator of this species, in that case a crustacean, and here which is also a crustacean. And they found these microplastics also in the predator, so they could see that they could be transferred from one trophic level to the other. And they've also done this in the field, where they sampled a location they sampled zooplankton species and fish, and also they checked in the feces of the seals to see if they could find the same microplastics, and they did, so they could link these microplastics between these trophic levels. And now I'm going to talk a bit about the freshwater environment. You will see that there is less data than for marine organisms, because for marine organisms there have been many more studies performed, and when it comes to freshwater systems, not so many species have been tested. But in general, the results are quite similar. So we can see this heteroaggregation between the microalgae and the nanoplastics. And we can also see effects of nanoplastics on the growth and the reduction of the chlorophyll content, and also in some other species, no effects were found. This species has actually been very well studied. Probably you've heard about this species before because it's very commonly used in toxicity studies. It's called Daphnia magna. And it's very interesting because even with the same species, different studies found very different results. And as I said, this depends on the size of the plastics, their shape, their charge. So that makes studying nano and microplastics very complex. And in this instance, they found effects on the mortality, a reduction in growth, in the neonate production and neonate malformations when exposed to nanoplastics. And this study exposed Daphnia magna also to nanoplastics, but they didn't find any effects. This study exposed them to microplastics, and they saw a reduction in the feeding and a reduction in their reproduction. When it comes to freshwater benthic invertebrates, there is almost no data. Now there is more because I generated it during my PhD, but at that time when I started, there was only this study where they found a reduction in the growth of Hyalinatheca, which is a shrimp. And for other species, they saw that they were able to ingest microplastics, but they didn't test effects. And also when it comes to vertebrates, they saw that fishes could, reduce their locomotion when exposed to nanoplastics and microplastics. And also for freshwater systems, a couple of studies have been done on aquatic plants, on sediment root microphytes, where they saw that there was a reduction in the shoot-to-root ratio, so the shoots were growing less than normal when exposed to microplastics and nanoplastics. And also in a water plant that lives on the surface, where they saw that there was a reduction in the root growth, also similar to what was found with the other water plant. They've also looked at trophic transfer. I actually like this study a lot because it illustrates very well how these nanoplastics can be transferred, how they heteroaggregate with the microalgae, and how they are ingested by Daphnia magna, and how they are ingested and end up in the fish larvae. So, do you think this would be enough to do a risk assessment for nano and microplastics, or do you think there might be some problems when you want to really know what's happening or how severe the problem can be? So I would like you to discuss this for a minute. Like, if you can tell me how this, if there are problems and how they could be improved to really be able to know more about the effects and what the risk is. you think this, it's very clear? Do you think, oh yeah, now I know what the effects are?
Maybe you can look at the composition of plastics, that some type of plastic has more influence than other types of plastic.
So you would think that maybe testing one species with different plastic types would provide interesting information. Yeah, I agree. That would be really nice. Someone else want to say something? Like, what do you think about the concentrations? Like, do you think it's good to just test one concentration? Is that providing a lot of information, or do you think it's interesting to have a range of concentrations? Or do you think, for instance, if these studies can be comparable, because one used sediment and they expose the sediment, the microplastics via the sediment, or others use yeah, one temperature, or yeah, different plastic types? What else would you do? Well, I can imagine it's quite complex, and this is what I saw when I started my PhD. These were the problems that I found with the data. Of course, there was a lack of data, especially when it comes to freshwater organisms. Also, that there were no standardized laboratory assays, as there are sometimes for chemicals, like how to test them in a way that the results could be comparable. As I said, if you use this species, do the exposure via the sediment or via the water, or the duration of the experiments should be this or that. Also, I saw a lot of unrealistic exposure scenarios. As I said, like very high concentrations of plastic, no natural food. Yeah, or as I said, testing a species that lives on the ventos and they don't add sediment but just add a lot of plastic. Also sometimes, which I didn't explain so much here because Bart already talked about the vector effect, in some studies they didn't really make sure that there were no chemicals at all in the plastic. And that's also important when evaluating the effects of plastic. You really need to know that the effects come from a physical effect of the plastic and not from chemicals added or absorbed to these plastics. And finally, the way, or the best way that we think these effects could be evaluated would be by detecting the effect thresholds in order to fit a dose response model. And what do I mean with this? So this is an example of a study where they tested the effects of microplastics on the photosynthetic efficiency of 3 algae species, microalgae, 2 of them marine and 1 freshwater, and they had 2 concentrations of microplastics and the control. And then this is what they provide, and that's very interesting, but what if they would have found that there was a difference between one concentration and the other? How can you really know when this effect is starting to happen? So for this, what is normally used are the effect thresholds. This is an example that I took from a study with microplastics. It's not the perfect example of how dose response curves will behave, but it's still interesting to analyze it. What they show is the concentrations of microplastics and how they affect the zooplankton species on the number of nappies that they produce per female. And if you have a wide range of concentrations, you can try to find these effect thresholds. And one effect threshold, the one that they are showing here, is EC50, which is the concentration at which 50% of the population will be affected, in this case by an effect on the nauplius production by females. Another effect threshold is called no observed effect concentration, and this would be the concentrations that would be found here, so the area where there will not be effects, and the lowest observed effect concentration would be in this case here, which is the same of the EC50. So by calculating these values, EC50, low wake, no wake, we can better know how these microplastics will affect the population. So, as I said, when I started my PhD, they told me, okay, our aim is to do a risk assessment of microplastics, and that's the aim of the project in which I'm working. And my part was to do the effect assessment. So what I thought I would first start measuring effect thresholds for different endpoints. And for this, what I would need would be a wide range of microplastic concentrations, a single stressor study, so I would really have to make sure that what I was testing was just the microplastics without chemicals. I also wanted to test different species, and in this case we were going to focus on benthic invertebrates. And we wanted them to have different traits, so different feeding strategies, some living inside the sediment, all others living on top of the sediment, feeding on different organic matter or on dead organic matter. So then I also wanted to determine the particle ingestion so that I could explain if I saw an effect that I could see that this effect was caused by the ingestion of microplastics. And I also wanted to have a standardized setup so that I could compare the results for the different species. And I wanted to simulate natural conditions by mixing these microplastics with the sediment. And what I did was to use polystyrene microplastics with a size range between 20 and 500 micrometers. And for this, I decided to test these 6 species. 2 amphipods, Gammarus pulex and Lateca, 1 isopod, Acerus aquaticus, 2 worms, Lumbiculus variegatus and Frugiferus species, and 1 bivalve, Styrene coreum. And for this, I did what is called single species toxicity test, which look like in the picture. So you have a beaker in which we added the sediment with the microplastics, and we added fresh water, and we added the species there for 28 days. We had 7 concentrations of microplastics, ranging from 0 to 40% of plastic for sediment dry weight, and we had 4 replicas of its concentration, and we looked at the endpoint survival and growth for 5 of the species, and reproduction for another species, because this species reproduced during the experiment, so this is the endpoint that is normally used. Also for 2 species, we checked for the feeding activity and particle ingestion for the 2 amphipods, the 2 shrimps. And for this, what we did for the particle ingestion, what we did was after the 28 days exposure, we allowed the organisms to defecate and to excrete all the microplastics that they have in their gut. And then we checked for the presence of microplastics in the feces and also in the body of the organisms. And in order to get the particles back, we added the organisms or the feces with H2O to a beaker, and we filtered this with an analyst filter, and we analyzed 4 areas of this filter with a micro FTIR, which told us how many particles there were in this area, what their particle identity were, and also what their sizes were. And I think we can maybe have a break now, and I will continue after this break with the results. Thank you.
Wat voor taart is het dan?